Alright, so I have a couple of announcements for you guys. So next week we're going to have our first midterm. So the midterm is gonna cover the determinacy and indeterminacy of structure, and it's going to cover deformation and deflection, and cables and arches, the one that we are gonna cover today, and maybe we're gonna spend next lecture on cable and arches, and I'm gonna post the homework for cable and arches to be submitted next week. So what do you guys prefer, Tuesday or Thursday for the midterm? Do you guys have any preferences?
Thursday.
Thursday?
No, for me Tuesday.
Tuesday?
Both for me.
Whichever is going to be easier.
Easier? No, it's gonna be the same exam, so all right, so I'm gonna decide after the lecture and send the announcement to you today. So as I said, it's gonna be around 3 questions, maybe 4, but I believe 3. 1 on static determinacy, 1 on deformations. So it's gonna be 1 problem. I don't know, maybe double integration, maybe conjugate beam. You should be prepared. And 1 on the cables and arches. Okay, so that's gonna be the exam. Right, so for who came late, we have midterm exam next week, and I'm gonna decide it's either to be Tuesday or Thursday, so watch out for an announcement. I tried to upload the lecture from last week on Canvas, but somehow Canvas didn't let me. I'm gonna give it another try today, okay? All right, so last time we started to talk about cables and arches. All right, let's write here. Analysis of cables and arches. And last time I drew something like this, and I said that this is a general cable, and this cable is supported by 2 hinges, and it has, I don't know, a bunch of loads, maybe its own weight load, something like this. And if we cut in this cable at any location, like here and this way, so first, to analyze any structure, you have to get reactions. So since all the loads are vertical, so I'm gonna have a vertical reactions like this. But since this cable, from the geometry, there will be a horizontal reactions, like all these loads wanna bring the cable down, so definitely there will be a horizontal load something like this, and a horizontal load something like this. Why? To balance the force in the cable, because this cable, for example, maybe this theta, like this cable is going down, so I'm gonna have a tension in this cable going this way, so I need a reaction in the other way. I have horizontal and I have vertical force to balance the tension in the cable. Same way here, this cable wanna pull the support down, so you need reactions on the other side to balance these forces. So we have horizontal, and we came up to a conclusion that this horizontal force, as soon as the cable doesn't have any horizontal loads, do you guys remember what is the tension in the cable equal to?
H over cosine theta.
H over cosine theta. So how did we come up with this conclusion? We said that we are gonna take a section in this cable, and if we cut in this cable, once you cut in a structural member, all the internal forces are gonna show up. Like it's gonna be, like my cable is something like this. So once I cut in this cable, the tension in this cable is gonna show up something like this. And it has 2 components, like it has, let's say this is T1, it's gonna have vertical component and it's gonna have horizontal component H. And from the sum of the horizontal forces on this section, like let's say this is H1, when we analyze this cross section, actually this cable has all the loads from above. It's hot, right? It's not cold, it's hot. Is it hot?
It's set at 70.
Yeah, it's better.
Okay. Because anyway, all right. So when I take this section out, so when I do static, make sure that this is stable. When I do sum of the forces in the x direction, I will find that H, the horizontal force reaction here, is equal to H1. Because there's no other horizontal forces, okay? If you cut in this section, you'll find that H1 also is equal to H4, H2, H3. So the horizontal forces are always equal to the horizontal reaction, as soon as the cable doesn't have any horizontal loads. All the loads are vertical. Okay, so I solved this one. How about V1? I can get V1 if I know the tension in the cable, like if I know T1. But to know this, I need to know the angle here. I need to know the slope of the cable at this location. From the slope of the cable, it's gonna have two components, like H component, H1 is gonna be equal to T1 cosine theta, and V1 is gonna be equal to T1 sine theta. That's from analyzing the forces. Okay, so if you know H1 is equal to H, so you definitely can find what is the value of T1. T1 is going to be equal to H1 over cosine theta, and H1 is equal to the horizontal reaction. So that's what we came up last time. In the last 10 or 15 minutes, we had this rule that the tension at any location in the cable is equal to the horizontal reaction over cosine theta at the location of interest. So if you want to find the tension in the cable here, try to find this angle theta. Once you find theta, divide the horizontal over cosine theta. If you want to find the tension here, find the slope of the cable here, theta. So that is what is going to tell you how much tension is this, how much tension in this cable. All right, so and then we started talking about where can I find the maximum tension? Do you guys remember? The maximum tension at the maximum theta, when the theta goes, until theta becomes 0. If theta becomes 0, when theta becomes 90 degrees. If theta becomes 90 degrees, so cosine theta is going to be equal to 0, and this value is going to be infinity. The tension is going to be infinity. All right? So that's the maximum. And what is the lowest when the theta is equal to 0? Like here, like let's say here, theta starts to be 0, so cosine 0 is going to be equal to 1, so the tension is going to be equal to the horizontal force. Okay, so we said that mostly the maximum tension at the support, because at the support we have the maximum theta. Okay, so that's where we are going to have a maximum theta. But I have two supports, so definitely it's one of them, and the one that has the maximum slope. So which one of these that might be having the maximum tension? This support, the tension here, or the tension here? Why? Because this is where I have the maximum slope of the cable, okay? All right, so let's put this to practice. So I have an example here. All right, I have this cable. The distances are 30 foot, 40 foot, and 30 foot. And there's a bunch of loads, two loads on this cable, 12 and 6 kips. I have concentrated load, 12 kips, kilopounds, and another one is 6 kips here. So what I'm asking for here, find the reactions and H2, okay. So I gave you H1 here is equal to 6 foot, but I didn't give you what is the value of H2. And I'm asking find the reactions and H2. That's what I'm asking for. Okay, let's name these joints. I have A, B, C, D. All right, so what is the reactions that I have here? I have two hinges. Each hinge is gonna have a horizontal and vertical reaction, right? So I have AY, and I have dy. And I have horizontal force, right? I have horizontal force I believe it's this direction. By the way, you can assume the horizontal force in the other direction, but it doesn't make sense. But it's fine, and once you finalize the problem, you'll find that horizontal force is equal to -50. That means your assumption is wrong and it's in the other direction. So it's fine if you assume the horizontal force in another direction, but from the sense, if you have a cable, this cable is pulling the loads down, so the horizontal force is going this way. And absolutely, since there is no horizontal loads, so H on the left is equal to H on the right, but you can assume them differently if you want. Okay, so I have the horizontal forces, so let's find the reactions. What do you guys think the best way to find a reaction? What equations should I start to? We all know what we know, what equations that we know about this to make it stable, statically determinant. It's a determinant. But how to make it stable? Like the static equations that I start with. We have some fx, we have some fy, we have some of the moment, right? This cable to be a structure, not a mechanism, it doesn't have to move in x, it doesn't have to move in y, it doesn't have to rotate, okay? But there's a better way to start with, like you can say some fy is equal to 0, but you will end up with an equation that has ay and dy, two unknowns. So I want to start with a static equation that only gives me one unknown, and then I move forward. So what equation should I start with? Moment, right? Excellent. So I have the solution. And you can start either the moment from the left or the moment from the right. So I can say the moment about A or the moment about D. So maybe I will say some of the moments about A should be equal to 0 if this is a static structure that doesn't move. And I can assume the positive direction maybe in the other way, because it's gonna make it easier. You can assume it in any way. Actually, assume in this direction, so we can have the same numbers. All right, so if I want to take the moment about this point, so what loads that make a moment about this point? The 12, the 6, and dy. How about h?
No.
Because it passed with the point that I take the moment at. So I have 12 multiplied by 30 foot plus 6 multiplied by 70, right? 30 plus 40 minus dy multiplied by 100. 30 plus 40 plus 50. And all this should be equal to 0. Once you solve this problem, you'll find that dy is equal to 7.8 gets. All right, I got the first one. If you want to find ay, you can take the moment here, but for me, right now, I can say some fy is much easier. Some fy is equal to 0, and I can assume that the positive is going up. So I can say that dy, which is 7.8, plus ay, this reaction, should be equal to 12 plus 6, which is 18, or I can put them here, minus 12, because they are in the negative direction, minus 6, equal to 0. Either are the same way. Okay, so you'll find that ay is equal to 10.2 kips. All right, I found both reactions. How can I find the horizontal force? You'll tell me, okay, we used all the equations. So you can say some fx equal to 0, right? We used moment, we used the fy, and then we are going to say some fx equal to 0. When you say some fx equal to 0, you will end up with h1 is equal to h2, right? But this doesn't solve the problem. Didn't tell me what is the value of h. What should I do?
And the tension in the cable.
And I don't know the tension in the cable yet. If I know it, I would use this equation to get the horizontal force. But if you guys remember last time, I told you one property about the cable, that the moment at any point, left or right, is equal to 0 because it doesn't take any moment, right? This cable doesn't take any moment. So if you take the moment about any point on this cable, either from the left or the right, should be equal to 0. Okay, so I can take the moment about B and from the left side, and I say it's equal to 0. Why? Because I know the height at B, but I don't know what is the height at C. Okay, so when I multiply h1 by 6, so it's gonna be only one unknown, which is h1. But if I take the moment about C, it's gonna be function in h2. So I will have h2 unknown and h, like the small h and the capital H, both of them are unknown, the height and the force.
Professor,
Sorry, again, why is it zero the moment on the left or the right side of the cable?
Because last time when we were discussing, cable is not like a solid cross section. Solid cross section, it resists moment, but cable is a flexible member.
Correct.
So it allows the moment at all the point on the cross section. Okay, so it only takes tension.
Correct.
It doesn't have bending moment. It can take compression. If you make a cable and try to compress it, no. So the moment at the cable, either from the left or the right, so all the points at the cable can be treated as intermediate hinge. You can take the moment left or right is equal to zero. That's one property about the cables. Okay, so what I'm gonna do, I'm gonna take the moment, the sum of the moments at B from the equal to zero from the left, and I'm gonna say that the positive is gonna be this way. So what forces that makes moment about B from the left? I have these two reactions, so I can say that H1 multiplied by the height 6 foot minus AY, which I got at 10.2, multiplied by 30 is gonna be equal to 0. Okay? So you will find that H1 is equal to 50, how much? 51? 51 kips. All right. And I want you to notice something that's actually very, very important property about cables. Look at this. I said for cables, the moment from the left or the moment from the side, like left or right, is always equal to 0. I can equate it to 0. That means this equation, like if I got here, I'm gonna say that the horizontal H1 multiplied by this height minus all the moment from the left or all the moment from the right equal to 0. I can do the same here. Like I can say sum the moment about C from the right equal to 0. And I can say it's positive this way. So when I say when I want to find H2, actually H2 is equal to H1. Like if we say sum fx equal to 0, so you will find that H1, and let's say that is the positive, so H1 is going to be negative, plus H2 is equal to 0, so H1 equal to H2 equal to 51 kips. Alright, so that's, with no say, very easy thing to do. So I know that H2 is equal to 51. So if I want to take the moment about C from the right, I have H2 multiplied by this height, and I found out that H2 is equal to 51, multiplied by the height 2, minus dy, I found dy 7.8, multiplied by 30 is equal to 0. So I have H2, after you solve this, is gonna be 4.6. 4.6. All right. That's what I got. That's actually what I'm asking for. Find the reactions. I got all the reaction and I found H2. Okay? So I want you to keep attention what I did here. As general equations that we used here and here, the horizontal force at any cross section, at any point, Z. So horizontal force is always constant, multiplied by the height Z at this point, minus the moment at Z is equal to 0. That's what we did here. If we came at this point, multiply H by this height, HZ, okay, minus MZ either from the left or the right is gonna be always equal to 0. Like you can't take it from the left, it's the same thing. From the right, it's the same thing. Okay? So I'm gonna talk about this in a little bit, but just to keep this stick in your head for a while. Okay, so the next step that I'm asking for here, compute the tension in the 3 cables. Number 1, that's number 1. Number 2. Tension in the 3 cables. Right, so I have three cables here. Let's get cable AB. So cable AB is something like this. I have a hinge here and the cable is going down. And I know this distance is 30 and this distance 6 feet. And what I want to find out, this is A and this is B, and I want to find out what is the TAB. Right, so right now we know the horizontal force, and if I know the horizontal force, the next thing that I need to find is theta of this cable, so I can find the tension of this cable. So we can say here that the tension TAB is going to be equal to the horizontal force over cosine theta at P. This theta. How can I find this theta? What should I do? Geometry, right? I know tan theta. Tan theta is equal to, it's going to be equal to 6 over 30. Then you get tan inverse of 6 over 30 on the calculator. And this is going to be equal to theta. And theta, once you find out, it's going to be, right, 11.31. Thanks. Degree. Right? So once I know this, so you can get TAB is going to be equal to 51 over tan 11.31, which is equal
52.
No, I need was fractions. 9/8.
52.
52 exactly. No, did you try the whole angle, not 11.31? So it's gonna be like 9/8 or something. Okay. That's cable number 1. Let's get cable number 2. So cable number 2 is gonna be something like this. So the tension at point C, let's do it here. Tension here, let's say TBC, and I'm gonna call this angle C. And I want you guys to tell me what is the heights that I have here. This angle is equal to this angle. I have this horizontal is 40 foot. How about this distance? If I want to find this distance, what should I do?
6 minus 4.6.
6 minus 4 point. It was 4.6. All right, so tan theta, or tan inverse 6 minus 4.6 over 40 is gonna give you theta, and this is gonna be the angle 2 degrees, right?
Is the height 5 feet?
Hmm?
The previous question.
What
The TAB.
TB?
TAB. When you solve for TAB.
That's
It was
51.986.
5 feet or 6 feet?
6 feet. This is 6.
And then the bottom equation,
30,
the black one.
51.
51. That was
That's
five.
the horizontal force.
Okay.
Okay, so this is case. All right, so when I try to find TC, this is B actually, BC. TBC is gonna be equal to H over cosine theta C, and this is gonna be 51 over cosine 2 degree, and this is gonna give me 51.03. Kips. All right, so let's find the tension in cable number 3. Okay. Cable number 3. So you're gonna have something like this, and this is the hinge, and I have CD, TCD, and I know this distance is 30, and this height is 4.6, and this is theta equal to the same theta here. So, and I can say that tan inverse 4.6 over 30 is equal to theta CD, and this is gonna be 8.7. 8.7, right?
Yeah.
Degree, and T CD is gonna be equal to the horizontal over 10 theta CD, and this is equal to 51 over 10 8.7, and this is gonna give us that the force is 51.62 kips. Right, I got all the tension in all cables. Look, this one is 51.62, this one is 51.03, this one is 51.98. So that's the biggest one because this is have the highest slope, 11.31. And if the slope gets less, like 8.7, it becomes 51.62. If the slope get more or less, it's gonna be 51.803. However, they are very close to each other. They are all of them almost to 51. Why? Because the angles are very, very small. So it's not big enough to make a change, right? Does anybody have any question?
Is that H over tangent or H over cosine?
This one? H over 10 theta CD.
I thought that's supposed to be cosine.
Oh, sorry, yeah, that's cosine. Sorry. That's the tan to get the angle, yeah. Cosine. That's cosine the angle, right?
There's also a tangent here.
I put
TAB.
tans here. Okay, but the numbers are right, okay? Cosine. Okay, this is one is cosine, right? This is cosine, okay. So yeah, I got all the forces in the cables. Okay, so let me start writing.
Is there a case where the H varies in value?
H varies in value?
Yeah.
What do you mean?
So like, is it,
If
it might not be 51.
If you have horizontal force on your cable, like if your problem, I give you your problem that this cable is has something like this. Has horizontal load, that's when the horizontal force here is gonna be different, and it's gonna be different at all the cable.
Gotcha.
Okay, but this is what never happened because if you did this to your cable is not gonna be stable. It's gonna shake. Cables can take vertical loads. It's not gonna take horizontal. If they take horizontal loads, it's not gonna be good. They are gonna be like a swimming.
And Professor, when we're doing, for example, PT cables, and we have a
Post tension.
post tension cables, and we have a long cable that needs to be stretched from both ends. In this case, sometimes by adding cables in a section, we have a force here and a force here.
Okay.
How come that doesn't make unstable the cables?
No, that's horizontal forces on the cable. That's reaction.
Okay.
That's you pull the cable with. That's how you anchor the cable. That's reaction, not load. So all the loads on the post tension cable comes from the concrete going down. Not there's nothing is coming this way, and they are stay still in their conduit.
Correct, but when you pull them, you're not causing the reactions of the cable?
You pull them so that you can make anchors, so that you can provide the stability. If you didn't pull them and you left them loose, they are nothing.
Correct.
So that's why you are making this hinge. You are pulling them, and then you anchor them. So that's why you can make this hinge situation.
Okay.
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 All right. Okay. So I just want to grab your attention to this rule. That do you guys remember? We said that the horizontal force multiplied by hz minus the moment at this cross section is equal to 0. We call this rule the general cable theory. The general cable theory. That's a very, very important theory, and that's actually what is special about cable, that the moment at any cross section is equal to 0. So I'm gonna put that here. So for example, yeah, so let's see how we can apply this theory, the general cable theory, in a very interesting way. Like, here's my problem, it's over there, like you, and then I have, that's my cable, and then I have load here 12, and I have load here 6. What can I do with the general cable theory? So the theory is telling you, if you draw the equivalent beam of this cable, like you make a beam, simple beam, hinged you put this load 12 and 16 on this beam, and then you draw the bending moment diagram on this beam. So the bending moment diagram is gonna be something like this. The value is gonna be $10.2 multiplied by 30. Okay. First, you can get the reaction on this beam. If you get the reaction on this beam, it's gonna give you the same, this beam. The same one on the cable. We got here 10.2 and we got here 7.8. If you got the reaction on this beam, you'll find that this is 10.2 and this is 7.8 as a beam, okay? And if you draw the bending moment diagram, you'll find that the bending moment diagram 10.2 multiplied by 30, and here is gonna be 7.8 multiplied by 30. That is the bending moment diagram. So the general cable theory is telling you, if you, this is horizontal force, and I have horizontal force here. If you multiply the horizontal force by the height at any cross section Z minus the moment mz, the moment at the beam is gonna give you 0. Okay, so when I give you a cable problem, this one, you draw the equivalent beam and you draw the bending moment from the load on the cable on this beam. If you wanna know the height here, you multiply the horizontal force by hz and take the moment on this beam and put it here and equate it to 0, and then you will find what is the value of hz or the value of this one. So like for example in this problem, we didn't know h, but we know the height here, which was 6 foot, minus the moment 10.2 multiplied by 30 equal to 0, then you can find h is equal to 51 kips. And then I can apply the same equation here at this cross section. So I can say that h multiplied by h at C minus the moment at C equal to 0. So h, I know it right now, 51, multiplied by hc, which I don't know, minus the moment at C, which is 7.8 multiplied by 30 equal to 0, and then you'll find that hc is equal to 4.6 foot. I solved this problem in just 2 steps. The whole thing. Like all what we did right now, I did it here. Like all these 2 ports, here and here, from static equations. How? You draw the equivalent simple beam of the cable, put the same load on the cable at the same location on the beam. Get the bending moment of this beam at these 2 points. Solve this beam for reactions. I got these reactions here, 7.8 at 10.2. And then what you are gonna do, you are gonna use the general cable theory that we have here, and then it's gonna be at any location, the horizontal load multiplied by the height at the location of interest minus the moment on the simple beam at the same location is gonna be equal to 0. So once I did this, I got the horizontal force. And then I did the same thing at the other location, and then I got the missing height. So that is what is good about the general cable theory. Actually, I proved the general cable theory here, so maybe you will have to read this page. So I made a cable. One of them has concentrated loads, one of them has distributed loads. And then what I did, I drew the equivalent beams on each one of these, and I used symbols, dragged them down until I proved that this is the cable part, cable coming from the cable, this is coming from the simple beam. I proved that the beam part is equal to the cable part. Okay?
The moment is taken from which point?
The moment is taken from the equivalent beam.
So and the MZ is the point.
The bending moment from the bending moment diagram of the equivalent beam. Like you draw an equivalent beam, you put the same load and deal with it as a simple beam. Once you deal with it as a simple beam, draw the bending moment diagram. Take this moment and put it here. It is the same thing. But you know what we did here? We take the moment from the right and equate it with h multiplied by h. What is, if we have a beam and if we want to find the bending moment, what we do? We cut at this section, calculate the moment from the right or from the left. So that's what we did here. So it's the same thing. All right, so that is called the general cable theory. Use it in the exam, it's gonna save you a ton of time.
So basically, if we want to do it with the graph, we just like put the forces on top of the cable, do it a beam. find
Like
the-
here at the core. Okay,
Yeah.
so what you are gonna do, like if I give you any cable, like any cable from here, like something like this, and I put a hinge here and a hinge here. From here to here, you're gonna make a simple beam, something like this. And then if has a uniform load, you're gonna put the same uniform load on the same beam. And then you draw the bending moment diagram.
Mhm.
So any moment on this beam, M, and then you have a horizontal force here, and if you wanna, and there's a height here, and you wanna find this height.
Yeah.
So at this location, you take this moment and make it equal to the height multiplied by this one. So H multiplied by HZ minus MZ is equal to 0. If you wanna do the same, you can come here. Make H multiplied by this height is gonna be equal to the same moment here, okay? Right, we're gonna solve a problem and apply the general cable theory right now so that we practice. And it's gonna have a distributed load, which is different from previous problem. Okay, so this problem, it's like a state cable bridge. Like in a state cable bridges, you have your bridge maybe something like this. This is the slab of the bridge. And it's like there's a tower column like this. And definitely, usually it's underwater, like this one is supported all the way down. But anyway, we're not gonna focus on this. Like our focus is not on the analysis of the slab, it's analysis of the cable that supports the slab. So I have a cable like this, something like this, and it is supported here and supported here, okay? And usually the load on this cable is distributed, like usually this cable is supporting the slab by small cables. So if we want to distribute this load over the cable, so it's going to be a distributed load, something like this. The value of the load that we have, W, is equal to 0.6 kips per foot. And the distances that we have here is 40, 60, 60, and 40. And what I'm asking for here, and this angle is 45 degrees. And this height, the sag, H is equal to 10 foot. All right, so that's all the data that we have for now. And what I'm asking for, find the maximum cable tension for BD. Okay, let's put the letters A, B, C, D, E. So what I'm asking for, find the maximum tension in cable BD. So this cable is 3 sections, AB, BD, and DE. And from the symmetry, anything that is for AB is the same for DE. So what I'm asking for, number 1, find maximum tension T BD. And number 2, find the tension TAB. So I want to find the tension in this cable and the tension in this cable. All right. So let's see how we can do this. So the easiest way to do this, I have this cable. is supported from here and supported from here. It's like a simple beam, okay? It's like you have all the load is just on this piece, and it's supported from here and here. There's no load here and there's no load here. I know that there's a reaction coming from here, like there's a tension here, that act as a reaction on this beam, like as a vertical reaction, like this is the action, okay? So we need to differentiate between action and reaction. This cable want a tension this way, okay? But the support is going up, making like balancing this reaction, okay? So if you take this one out and make something like a simple beam, like let's put this is as a simple beam, something like this, and it has a load, something like that. So what is the bending moment is going to be look like on this beam that has W.6 kips per foot? The bending moment is going to be WL squared over 8, right? There's going to be something like this, and in the middle is going to be WL squared over 8. So from this, we can use the general cable theory, say that here in the middle, H multiplied by H at C minus the moment at C is going to be equal to 0, right? So I don't know what is the horizontal force in the cable, but I know the height at C, the sag, is equal to 10 foot minus the moment at C, which is WL squared over 8, W is 0.6, L is, by the way, this is all the L, so it's going to be 120 squared over 8. All this is going to be equal to 0. You will find that the horizontal force is going to be equal to 108 kips. I need this to solve the problem, okay? All right, but this is not what I'm asking for. What I'm asking for, find the maximum tension in this cable. Okay, first I need to locate where is this maximum tension, and then I need to know what is the value of this tension. Okay, two things. The first thing, where's the maximum tension in this cable? B, C, D. Where is it? It's gonna be either a B or D because it's symmetry. Here is the minimum. Here is the maximum because that's the maximum slope. So I know T tension here is the maximum, all right? And I want to find this value. Okay, let's find this value. How can I find it? To find it, you need to find theta, right? So I need to find what is the value of theta here. Or I need to find what is the value of tan theta. If I found the value of tan theta, I can do it. To do this, you have to find what is the equation of this line. Okay, let's find the equation of this parabola. If you have a parabolic curve like this, okay? And let's put XY coordinates here. And I know, let's put it symbols, like I'm gonna put L over 2 and L over 2, and this is H. If you wanna find Y as a function of X, do you guys know how to do this? First, this is a parabolic curve. The XY axis at the center of this parabolic curve, so it has an equation equal to, the general equation of a parabolic curve is going to be y ax squared. If this is shifted, so definitely there's a constant b, but it's not shifted, so there's no constant b. Okay, so it's y equal to x squared. So to find the value of a, I need a boundary condition on this curve. I know at L over 2, the height is equal to h, right? So I can say at x equal L over 2, the y is equal to h. So I can substitute here and I can say that h is equal to a multiplied by L squared over 4. So a is going to be equal to, it's going to be 4h over L squared. I found the constant. So I can say that y is going to be equal to 4h over L squared multiplied by x squared. Substitute here. So I found the general equation of this parabolic curve. Right now, I can find tan theta. How? At any point. Tan theta at any point is going to be equal to the slope, right? At any point, if you want to find tan theta, you differentiate this function with respect to x, right? dy dx. So if I differentiate this function with respect to x, it's gonna give me tan theta, which is the slope at any location x. So if I differentiate this, it's gonna be, it's gonna be 8h over L squared multiplied by x. So right now I found tan theta, the general equation of tan theta. If you put this here, like if you wanna find tan theta at 0, so you're gonna put x equal to 0, so the whole thing is gonna be equal to 0. But I don't wanna do this. I wanna find it at L equal L over 2. So if you wanna find here tan theta, what I wanna find, tan theta at L over 2, because this is where x and y, where I put x and y, okay? So I wanna find it at L over 2, either here or here. You can put it negative, okay? It's gonna be the same thing. Okay, so I wanna find tan theta at x equal L over 2. This is gonna be 8h over L squared, and here we're gonna have L over 2. So this is gonna give you 4h over L. So right now I can substitute tan theta, and L over 2 is equal, or we can put L, like, actually we can do it here. 4h is 4 multiplied by 10, and L, by the way, L is all this distance, 60 plus 60. That's why I didn't want to do it here, so I don't confuse you. 120. So this is gonna be equal to 1 over 3. So when you get tan inverse, you'll find that theta is equal to 18.43 degrees. So I found theta, okay? Right now, I'm ready to get the tension TBC. And it's maximum because it's at this point, it's gonna be equal to the horizontal force over cosine theta. So the horizontal force, I found it 108, and theta is cosine 18.43. So this is gonna be equal to 113.8 kips. I got the first requirement in this problem, which is the tension in this cable. Actually, the second tension, what he's asking here, tension AB, that's a very, very simple. How? Right now I know the horizontal, and I know the angle. The angle is constant on this cable. It's a 45 degree. So the tension TAB is gonna be the horizontal force over cosine theta. So the horizontal 108, and I know cosine 45 degree. And this is gonna be 152.76 kips. That one was much easier. Does anybody have any problem? The horizontal force in this cable is the same because there is no horizontal load. Here is the same like here, everywhere. It's all what it changed is the vertical. Or we can say like this, the tension is it changing. The tension in the cable is it changing. All over here. Horizontal is constant, so the vertical force it changes because the vertical loads are changing. Okay? And tension is not changing here because theta is constant on this cable. Theta is not, it's all 45 degrees, so it's all constant. If you got it here, you'll find it the same way here. Does anybody have any questions? So right now in cable problems, what you are gonna do, you are gonna try to figure out how to apply the general cable theory. Try to draw the beam that is equivalent to this cable and try to use the bending moment of on this beam with the given heights in your problem to figure out what is the horizontal force. Okay? Okay, so that is for cables. Let's now talk about another topic. By the way, in real life, this cable, like when you solve this in real life, like you are gonna solve a stay cable bridge, you're not gonna give in this load. Like the thing is, you're gonna have like small cables holding this bridge from here and holding this from here, and you're gonna have load here and a load here. So what we do is to find how to transfer this load to this one. So it's either you put it as a concentrated load, but usually you have hundreds of cables and it's almost a distributed load. Or you can when you solve in the software, you put them as a concentrated load. So you'll find that the bending moment is like a small broken lines that is gonna make a problem. So it's either that you simplify as a distributed load, or you can put as concentrated loads. And then you solve this cable. So when we do this, first we solve the slab. And then once we solve the slab, we solve these small cables. And once we solve these small cables, we solve this cable. Okay? All right.
Do we include the self-weights of the
Mhm.
cables as well?
What was that?
The self-weight.
Yeah, well, some people neglect the self-weight, but this one, you can't neglect the self-weight of this one. That's a really huge cable. It depends on your bridge. Sometimes the diameter of this cable is like 1 meter.
Oh.
Like if you look at bridges like a Golden Gate Bridge, it's like this cable is like very huge because it's 2 miles or 1.5 mile the span. Same thing at Kashikayu Bridge in Japan, something like this. It's like one of the ones that are like 2 kilometers span. The span, I mean like the span between these two. And this column actually is like the height of Eiffel Tower. Like it's a very, very huge one. Maybe you guys go and search about Cable States Bridge, you will find a lot of interesting things. Okay, so right now let's talk about arches. So you guys, I believe that all of you know what an arches is. But let me get back to the same topic that when we were talking about cables. Why do we use cables and why do we use arches? Why we just use beams? Do you guys remember? We had conversation about that. Why we use cables and arches? Because that's the thing. When you are an engineer and you are deciding, you have to make a case that this system can't be a slab or can't be a flat slab or can't be a beam, or this system needs to be an arch system. Why we use these two? Okay, so let me bring us to the same topic that we were talking about like last week. We use systems that is gonna be efficient, depends on the space that we have. And as a structural engineer, our enemy is the bending moment. Bending moment is like a snake. It's not tension, it's not compression, it's like trying to transform between these. So it put compression in your cross section from the top, and then you will have tension in the bottom. So you have to face it in 2 ways. You have to use concrete and you have to use a steel. Okay? So it's like a snake. And the way that you are a better engineer, the way that you make the bending moment less, try to get rid of the bending moments. Okay? But these systems to build, it needs lots of efficient labor. So that's very expensive. So you need to justify this. If you are gonna use people that is gonna build a cable system or an arch system, so it's gonna be, you have to pay more for labor to save material. So you need to balance between both of them. These systems are gonna save you in material, but the labor is gonna be more expensive. However, simple beams or the regular systems, the labor is cheap and the system is a little bit expensive, okay? Okay, so as an engineers, we wanna get rid of the bending moment. So that's why, okay, let me ask you, what systems that doesn't have bending moment or has almost 0 bending moments? Trusses, right? We use trusses because it has tension compression, and this is try to make the bending moment 0, okay? But the trusses is like, it's rather than having a beam like this to hold your system, and you put all these materials inside, however, you only need tension here and compression here. So what you do, you said, okay, what I'm gonna do, I'm gonna put steel here, I'm gonna put a steel here, I'm gonna put something like this. And when this truss bend, all this is gonna take tension, all this is gonna take compression. So the truss takes the tension compression and utilize all the material that we have, okay? And we put cross members to make the truss stable. So that's why I didn't waste the material that I have here from the concrete section, okay? All right, that's one system. What other system? This one, the cable system. It only takes tension, but it's not like truss, doesn't take compression, okay? And has all moment equals 0. Also arches, somehow arches can have 0 bending moment. Arch systems, let me write this. Arches use material efficiently because applied loads creates axial, or let's say mostly axial compression on all cross sections. All right, the thing is, let's say that we have this space and the span from here to here is like, I don't know, 20 foot, okay? So you have a span that's 20 foot. And you need to cover this space. There's different ways that we can cover this space, like to make this slab. It's either you make a simple beam from here to here and make something like this, right? Or you can, what I'm gonna do like something like what we did here. Tower, and then we hold this with cables. You'll tell me, but right now I have a slab and I have cables. The thing is, this slab is gonna be very thick. If you put cables that support this slab at these locations, the slabs can be thin, so you can save material. Or you can make, you wanna cover, like I'm sitting here and I wanna cover this area, you can make an arch from here to here. But the arch can be in different ways. You can make it like this, or you can make it like this, or you can make it like this. There's different shapes of the arches, but there is only one shape of the arch that can have zero bending moment on each cross section. All right, if you go down, this arch is tending to be a beam, right? Once we go down, at some point it's gonna be beam and take full bending moment. But once we go up, this arch is going up, is gonna be less bending moment, okay? So we wanna find out that the arch, let's call it that way. Not all arches have pure axial loads. So it's not like cables. Cables definitely is not gonna take any bending moment at all. Arches somehow can take bending moment, depends on the shape. So it can be and cannot be. Definitely not the same value of the bending moment of the beam. Once this is getting curved, it's taking less bending moment. It's getting more curved, it's taking more less bending moment. Okay, so what I'm saying here, not all arches have pure axial loads. Designers can establish an arch shape is called funicular shape. If an arch is funicular shape, that means it has zero bending moment. So funicular arches is the zero bending moment arches. Try to remember this word, because maybe in the exam I'm gonna tell you build a funicular shape arch, and I give you the example and try to make, when I say funicular shape, that means implicitly I'm telling you that all the bending moment on the arch is equal to zero. I don't have to tell you build an arch that has bending moment equal to zero. If I said build a funicular arch, that means all the bending moment should be zero. In which, the funicular shape, in which all cross sections are in direct compression and moment is zero. All right, so let's see how we can build a funicular arch. All right, so if you want an arch to be funicular, it have to be the same shape of a cable. Like, let's say, if you have a cable like this, and it has, for example, let's split it into equal pieces. Let's make it. This is cable, and it has loads B1, B2, B3, B4, P5. And this is H1, H2, H3, H4, H5. What is special about cable? The cable are always under the general cable theory. That is the H multiplied by HZ minus MZ equal to 0. That's what makes a cable cable. If this rule is not applicable, that means this is not a cable. And the cable is taking a moment. There's a moment on this cable, okay? All right, if you wanna build an arch that is funicular, so it should have bending moment is equal to 0, the same way the cable is. So if you inverted this cable the other way, and make the arch something like this, and this height is the same heights like here, H1, H2, and actually let's make it symmetric, H1, H2, H1. And let's say this H1, H2, H3, and this one is H1, H2. If this height is the same like this height, and our arch is like this arch is a funicular shape. So, for an arch to be funicular, it has to be going with the general cable theory. It should be applied on both of them, okay? Because that's the same height and it's gonna be the same horizontal force, so all the loads are vertical. So for a funicular shaped arch, it should be the general cable's theory should be applicable, equal to 0. If this is not applicable, this arch is not a funicular shape. So let's solve an example very quick. So that you understand what I mean. It's gonna be very easy. Giving you an arch like this. The arch is hinged here and hinged here, and there's an intermediate hinge here. And there's a bunch of load on this arch at these points. Right, I have a load 30, 60, 60, and 30. And the distances are 30. All of them. 6 distances at 30 foot. So what I'm telling you in this, establish the funicular shape. Okay, so I give you the height. This height in the middle is 36 foot. The height in the middle is 36 foot. And here's unknown, H1 and H2. I don't know them. And I'm telling you, in this problem, establish the funicular shape arch. Example. Establish the funicular shape of the arch. Alright, so if you don't understand what is funicular shape is, you will not be able to solve this problem. I'm telling you directly, make the shape of this arch is funicular. That means all the bending moment are 0. So what I'm telling you, find H1 and H2 such that it makes the moment in all the cross sections are equal to 0. Find H1 and H2. And that's very easy. We're gonna do the same thing that we did for the cable. Take this arch, draw the bending moment like a simple beam. The simple beam that is equivalent to this arch, and put all the load. I have 60, 60, 60, and 30. If you got the reaction, okay, 360, 180, okay, 5 by 6, 300, 360, so you'll find out that you have 180 kips here and 180 kips here. And if you want to find the bending moment, the bending moment is going to be something like this. Point here, point here, point here. So I have moment at this point, moment at this point, and thing, same thing here, here, and here. So the bending moment is gonna be something like this, and when you find the values, it's gonna be 4,500, 7,200, and here 8,100, and it's symmetric. Okay, that's the bending moment diagram of the equivalent beam. So it's very easy to do it. How? First, I got the reactions already. Like here, the reactions is 180, so it's the same thing here. If you try to find the reaction, it's gonna be 180 here and 180 here. And if you want to find the horizontal force, there's many ways to find the horizontal force. Okay, that's different from the cable. Like the cable are all pulling down, so the horizontal force is something like this. The cable is from the top, so the horizontal force are going this way. Okay, so the cable wants this support to run this way, so the support is going this way. In the cable, the supports wanna go in, so the reaction is gonna go out. Okay, so right now I got a reaction. So to get the horizontal force, there's different ways. Actually, there's one way that you have an intermediate hinge here, take all the moment from the left is equal to 0, and you can solve this. However, I can use actually the general cable theory. It says that h minus h here, h multiplied by h minus mz is equal to 0. So I want to know the horizontal force, h, and I know this is 36, minus the moment in the middle, which is 8,100. All this is equal to 0. This only applies if I'm saying that this arch is funicular, okay? Okay, so once you solve this, you will find that h is equal to 225 kips. Do the same thing, but it's gonna take you some time. I mean, like, because you have to take the moment of 180, the 30, the 60, the 60. But actually, I did the same when I was getting the bending moment for this beam. Because you put all the load and you're trying to get the bending moment here, you get the moment from the reaction, the 30, the 60, the 60. So it's the same thing, okay? But drawing the beam is gonna make you solve for h1 and h2, the same thing. All right, so I applied this to get the h. So to get h1 for 0.1, I can say that h multiplied by h1 minus the moment at 1 is equal to 0. So right now I know the h is 225 multiplied by h1 minus the moment at 1 from the equivalent beam, which is 4,500. All this is going to be equal to 0, so h1 you can get it. 4.2, same thing. H multiplied by h2 minus m2 is equal to 0. I know h is 225. I don't know h2, but I know the moment here at point 2 is 7,200, and all this is equal to 0. So right now I can get what is the value of h2. So when you solve this, you will find that h1 is equal to 20 foot, and h2 is going to be equal to 32 feet. Does any of you have any problem with that? So I solved this using the general cable theory. So let's do step by step. This is your arch. I draw the equivalent beam. I put the same load. I got the reactions, and I got the bending moment. And then I used general cable theory at point 1 and point 2 and point 3. This one has the known h, but the unknown is the horizontal. I got the horizontal load. Since I got the horizontal load, I can use this to get h2 and h1. You can do this without even using your knowledge about arch. How? Like you can say, definitely the moment here is 0. So you can get h, okay? And since I said it's a funicular shape, so definitely all the moment at all these points should be equal to 0. So you can't take the moment here from the left and get what is the height here, and take the moment here from the left and get what is the height here without even knowing all this. Why is this? Because I said it's a funicular shape. If I said it's not funicular shape, you never can assume that the moment here is 0. There may be some moment here, okay? All right, does anybody have any questions?
For the movement on the beam, the distance is 6 or 30.
Here,
Yes,
this moment,
the x distance.
this here,
Because I'm finding 900 for the moment.
here.
At each point, so assuming like yes.
This is 4,500.
So the distance, the x distance, how much?
The distance is 6 multiplied by 30 foot. This is 30, 30,
Oh.
30, 30, 30.
Okay.
So when I say 6 at 30, that means it's equal 6 distances at 30 foot. Right? Okay, see you guys next time. I'm gonna end the topic of arches with solving one arch, and then we will do a new topic, okay? All right, you guys, I'm gonna send an announcement with the new homework and with the date of the midterm, okay? See you guys on Thursday.
The new time is